Thank you very much, Paul. It's a pleasure to be here, and thanks to all of you for showing up to listen to our various talks this evening. Like you, I've studied the program reasonably carefully. You can see it up there on the screen. I think I've been forced to conclude that I'm probably the warm-up guy at the start. Nevertheless, I think I have some very interesting things to tell you about cosmology, so that's what I'm going to spend roughly half an hour doing before we move on to the other talks. So, this is the picture that we often show of the entire history of the universe. I'm going to explain a few parts of that as we go along, starting from the Big Bang, way over on the left-hand side of the plot, and working up to the present on the right-hand side. The aim of a cosmologist, of course, is to try and understand all aspects of that diagram and figure out how we got from the Big Bang at the start all the way up to how the universe looks at the present. So, what you might call this is the cosmological quest. And I should say that cosmologists around the world nowadays tend to work in quite a collaborative manner. We all have common goals, we work together in different teams of different kinds. But we have a very clear aim in that, which is that what we want to do is lay down a theory of cosmology that may last a considerable distance into the future. Now, if I look at different science subjects, they always tend to have a time when they're developed, say, to a level which is understandable to undergraduates. For something like electromagnetism, that happened a long time ago, way back in the 1800s. For quantum mechanics, this was in the early 1900s. And really, since those subjects were laid down in these days, the way we teach them to our undergraduates has hardly changed at all. If you wandered into an electromagnetism lecture in 1,000 years' time, you will probably still be faced with Maxwell's equations and trying to understand what magnetism is. Cosmology's not been like that. I've taught cosmology for many years, and we keep learning new things about the universe, which force us to revise our lectures and change our descriptions, such as, for instance, the discovery in 1998 that the universe's expansion appears to be accelerating, where previously we'd all assumed that it was probably slowing down with time under the influence of gravity. So at the moment, things are evolving quite rapidly, but our hope is that we're now making substantial strides to understanding and fixing our understanding of cosmology. And I want to mention that that is really because of three separate things that are all coming together simultaneously for us. Certainly, it being driven by observations is very important. You can't learn much about science unless you can observe things. And we've been very fortunate in cosmology that starting 2 or 3 decades ago, it became apparent that a lot of the questions we'd like to address in cosmology could be answered with sufficient investment in projects like large telescopes, satellite missions such as the Planck satellite, whose results you see all around me, and other things like that. Projects take a long time to develop, so we've been seeing the fruits of those investments going back 2 or 3 decades just within the recent years, and that's really driven forward the way we understand cosmology. However, observation doesn't take you all the way. You need theory as well, and I should say I'm predominantly a theorist. Most of my work is theoretical, computational in various ways. And it's been very important for us that we've been able to develop theoretical models that seem to be able to explain the observations, and that's developed more or less hand in hand with the observations. In cosmology, we've been rather lucky that way. In a lot of subjects, you find that observations or experiment and theory can be at quite different stages of development. So, for instance, in some parts of particle physics, like string theory, you find that theory is extraordinarily well developed, but there's no way of carrying out any experimental verification. Whereas in some other subject areas of physics, experiment runs way ahead and measures phenomena that you have no hope of trying to understand with the theories we have just now. But in cosmology, there's a nice balance between the two of them. The other thing that's been very fortunate for us has been the development of computational facilities. High-performance computers, first with hundreds, now with thousands or tens of thousands of computational cores. The problems we face to make predictions from our models are very computationally intensive, and without these facilities, we would not be able to make any sort of progress, either in making our theoretical predictions or analyzing the very complicated data sets that we're now able to get. So these three things, I think, all coming together are what's made cosmology a subject that can move forward during these decades. Now, first I'm going to get past a very minor bit of jargon. What is a model? Inadvertently, people like me often mutter about models of cosmology, standard model, standard cosmological model. So I just wanted to remind you what I might mean by a model. It's not usually a physical thing lying on a table, but more it's a mathematical construct. It's a set of ideas and equations with which I hope to capture some aspect of the real world, in this case, the whole universe, Obviously, we're always simplifying, trying to cut things down to its basics, trying to find models to explain certain things, but not everything at once. But models are the currency of physics, and comparing models to observations is the routine work that we all want to do all the time. I wanted to mention it because I have to highlight two different aspects to how you make a model. One of them is you have to have clever ideas. Definitely a good thing. Everyone wants to have clever ideas, right? Here's some very clever ideas. A theory of gravity, such as Einstein's theory of general relativity, sets the framework for cosmology. The hot Big Bang, quantum mechanics. These are all fantastically important ideas that set the framework with which we try to understand the world around us. But clever ideas are kind of thin on the ground. Maybe once a decade, someone somewhere in the world has an idea of that sort of caliber. So clearly, if you're a working cosmologist, someone like me, your normal currency is not to think of the clever ideas. I must be doing something else. I can't possibly be spending all my time trying to develop completely new physical laws. So instead, most of us spend all of our time on the second aspect of a model, which is the parameters within the model. So for example, special relativity, Einstein's first theory from 1905, very good theory, tells us that space and time are united into a single construct called space-time. We can understand all of physics within that environment. Tells us that the speed of light is a constant in all reference frames. Very important principle, but what that clever idea does not tell you is what the speed of light is. Special relativity would be just as good a theory if the speed of light was 5 miles an hour, and then you'd have to worry about relativity just as you walk to the chemist down the road. It happens that it's an enormously large number, and it doesn't normally impact our everyday life, but it doesn't have to be that way. And the only way you find that out is to actually go and measure what the speed of light is by some method. So parameters are things which are left over once you've had your clever ideas. And much of what we're trying to do in cosmology is determining the parameters within the overarching framework. And I've written down a few examples on that slide there. Now, if a model is going to be much good, I should just mention in passing, it should be consistent with observations. Now, probably not all observations. You have to decide what things you're going to try and explain at a given time. But you want it to be consistent with the observations you have, otherwise it's not much use. But also, we quite highly value the predictiveness of our models as well. We like our models not just to tell us what we've already observed, but to make some kind of prediction for things we might observe in the future. And we tend to feel very good about ourselves if subsequently we make observations that then confirm the sorts of predictions that we've made. There's no obligation for a model to be predictive, but we certainly like it. So, what is the cosmological model I'm going to be talking about? I've divided it up into 3 parts. So these are the way we understand our universe in general. These are the clever ideas, if you like. So we have the hot Big Bang cosmology, which became the favored model way back in the 1960s or so. And the hot Big Bang cosmology is supposed to describe the overall properties of the universe, what it's made of, how fast it's expanding, what the shape of it is, other things like that. However, in order to attack that problem, we discover we have to learn about different kinds of physical processes, particularly what's known as structure formation in the universe. It turns out that structure formation is actually the key to understanding the properties and composition of the hot Big Bang model. By structure formation, I really mean anything in the universe which has formed in some way, like a galaxy, for example, or a group of galaxies. That could mean stars or planets. Any sort of structure which has developed and evolved as the universe is going along. And I'll look at that in more detail. I'll look at all of these things in more detail in just a minute. Finally, I'm going to mention only briefly, but it's one of my favorite topics for my own research, so I did want to mention it, is that we have a thing called the inflationary cosmology, which is our theory for how structure formation got started, the origin of galaxies and ultimately stars, planets, people. We believe is in quantum fluctuations which took place during a very early stage of the universe's expansion, a rapidly accelerated expansion that we call inflation. And I'll try to highlight just a little bit of the evidence for why cosmologists think that inflation is a good theory and why it may explain everything around us. Now, there's one thing I want to get out of the way before we go any further, which is everything I know about how or why the Big Bang happened. Okay, that's done. And the reason for saying that is, as an astronomer, I have absolutely no idea how or why the actual Big Bang happened, the actual moment of the explosion. I'm not even sure it's possible in principle to learn via astronomical observations what might have happened in the supposed instant of the Big Bang. What I do know is that the universe very much looks as if it had its origin in some kind of primordial explosion and has been expanding ever since then. And what I hope to understand is the properties of that expansion. So when I say the Big Bang, and when most cosmologists say the Big Bang, they usually don't actually mean the bang of the Big Bang, they mean the aftermath, all the stuff that happened afterwards. If you want to get to the actual bang of the Big Bang, then I think you have to go to theoretical insight rather than observational insight. And I imagine it's possible we may hear a little bit about that later on today. I don't know, but I have nothing to say on the topic that I haven't just said. I'm going to quickly skate through in slightly more detail the three pillars of the standard model of cosmology again. There's the hot Big Bang, and the hot Big Bang idea has been around for a long time. The expansion of the universe was discovered really by the guy on the right, Vesto Slipher, but he didn't really claim very strongly that that's what he'd found, and it was Edwin Hubble who came along a little bit later and mostly using Slipher's data concluded the universe was expanding, and ever since the expansion's been known as Hubble's law rather than Slipher's law, which is a bit sad. But anyway, they discovered the universe was expanding, and Einstein's theory of general relativity is a very good way to explain that expansion of the universe. So that's the framework. What are the parameters associated with that I might want to figure out? Well, for me, the challenge is to figure out the material composition of the universe. What is it made of? What's the budget of the different things within the universe? And we believe that the universe is made of 5 things. And again, I'll spell out a little bit more detail later on in the talk. Not a huge amount, I fear. But we believe the universe is made of 5 different things. The first of these, we call baryons, is the stuff that we're made of. Protons and neutrons and electrons. I can already see Brian Cox twitching away because electrons, we all know, are not actually baryons, but lazy cosmologists think, well, there's 1 electron for every proton. We don't normally have to consider them separately, so we lump them all in together. But atoms and us are made of the baryons. But that's just a small fraction of the total stuff in the universe. Then there's radiation, sometimes known as photons. Some of that radiation is the light emitted from stars like our sun, but actually most of the radiation in the universe is a relic from the hot Big Bang itself, the so-called cosmic microwave background radiation. If you added up the energy, the total energy budget of radiation in the universe, most of it is in that form. Very low energy radiation, but an awful lot of it. There are particles called neutrinos, very light particles. We believe the universe is filled with them. We have no way at present of directly detecting these particles because they are so weakly interacting. They happily zip right through the Earth as if the Earth wasn't there. But nevertheless, we can infer their existence by looking at the way in which structures develop in the universe. So we can be pretty confident the universe has got a pile of neutrinos in it. And then as we work down this list, we get to dark matter and dark energy, which are 2 separate concepts that we have in our standard models. And this is where someone like me has to start getting a little bit uncomfortable, because at this point in the talk, I have to tell you that in the universe, we don't understand all of the properties of the universe. In particular, there's 2 kinds of stuff in the universe we don't really understand. And not only that, but they're the 2 most abundant things in the universe as well. Dark matter is measured around here to be, for those who can see around the corner, about 27% of the energy budget of the universe. Dark energy is measured to be almost 70% of the energy. And in fact, the stuff we're made of is just a very small fraction of the total matter. So that's what we believe is there, and I'll show you some evidence for why we believe it's there, but clearly a little bit embarrassing to have that breakdown of things. Second topic is structure formation. The universe evolves, that's very important. It continues to evolve. We shouldn't think that the present universe is somehow finished. It's all over now, and we just look at whatever's resulted. We continue to see the universe evolving, and the main driver of that evolution is gravity. Gravity likes to pull things together, so if you've got a bunch of galaxies, they're all exerting gravitational attraction on each other, they will tend to come together and clump. This little simulation I've got here shows the formation of a cluster of galaxies, with any luck. or maybe not with any luck. Did it actually run? So my movie is going to fail to run. Oh no, there it goes. It runs over there. That's lucky. So the movie shows the development of a cluster of galaxies where the initial matter is spread out and is then drawn together. And we have to include other physics if we want to model this in detail, but to a first approximation, gravity is the driver of the evolution of the universe. And hopefully you can already see that this process of gravitational collapse can be the key to understanding some of the properties of the universe. For example, if I want to measure how fast the universe is expanding, well, the faster it's expanding, the stronger the expansion will be acting against gravity, and it will be harder to form structures if the universe is expanding faster. If I want to measure the total density of material in the universe, then if I've got more stuff, the gravity will be stronger, structures will develop more dramatically with time. What I have to find is the right balance of these different properties that match the observations I can make of galaxies and how they cluster together. The final ingredient is the inflationary cosmology. And as I said in my intro, this is what we believe created the seeds which later grow to form galaxies and other structures, and were laid down by quantum processes when the universe was very young. So in our map of the universe, the history of the universe here, the inflationary period is this very rapid expansion here when the universe was young, and then much later the universe evolves, things like the cosmic microwave background are created, and so on to the present day, which lurks way over on the right-hand side of this plot. Again, if we can learn something about the detailed form of these seeds, the initial structures, then hopefully we can learn things about physical processes that took place in our universe. So, precision cosmology is what I want to move on to. We're often said to live in the era of precision cosmology, and I stress hand in hand, this is precision observations and it's precision theory. You can see various things there, including some of our hosts at the moment that's in front of the COSMO supercomputer, which lurks somewhere over that way, I believe, somewhere, and various telescopes. Now, all I think I've got time to do here is just to highlight to you the sophistication with which some of the computer modeling is done. So I'm going to show you a simulation. I'm not sure whether people at the back can control the lights, but it might help to dim the lights a little if you can for this next movie. Thank you very much. This is a simulation of the endpoint of a study of gravitational collapse, showing individual galaxies, or at least the dark matter which will host the galaxies. I just want to draw your attention to how detailed these simulations are. The simulation involved about 10 billion separate particles being moved according to gravitational attraction, so roughly as many particles as there are people on the planet. It was carried out on 500 processors in Germany in this case, and took about 2 months to carry out the complete simulation. So overall, it's about 1,000 months of computation goes into that. As it happens, 1,000 months is about the average human lifetime. And I have to say, it never sounds like very much when you say it's 1,000 months, but it is 1,000 months, so use your months wisely. And you see the very detailed structures in that simulation, which we want to try and set against observations of different kinds. There. The observations I'm going to talk about, though, are not observations of galaxies, but the cosmic microwave background, which has proven over now many years to be the centerpiece of precision cosmology. We can make very precise measurements, but also the theoretical interpretation of these measurements is relatively simple. So cosmic microwave background, it's radiation left over from when the universe was young. It's the hot Big Bang. It starts out hot, it cools down, eventually atoms form, and at the time atoms form, the leftover radiation is released, and it continues to cool as the universe expands. We detect it on Earth. Its temperature is only about 2.7 degrees above absolute zero. So it's very, very cold radiation. It's in the microwave part of the electromagnetic spectrum, which is why we call it the cosmic microwave background. It was discovered in 1965, and it was already realized around about that time that the microwave background should carry towards us a photograph of what the universe looked like at that time. The radiation is released, and it just travels freely towards us where we detect it on or near the Earth. And so it really is literally a photograph of what's happened in the early universe. Now, what it should be a photograph of is the early seed irregularities that later form galaxies and galaxy clusters. And so that began a long search to discover these seeds, and eventually in 1992, a satellite called the COBE satellite, led by these two guys, managed to discover the irregularities in the cosmic microwave background. Now, the cosmic microwave background is very cold, as I said, 2.7 Kelvin, that's above absolute zero, but the variations in temperature are only about 1 part in 10 to the 5 of that. They're measured in microkelvin, or tens of microkelvin. So you need extraordinarily sensitive equipment to be able to measure these. But nevertheless, this was first achieved in 1992, and then later on, measurements became more and more refined, and until last year, the state of the art was a survey carried out by a satellite called the Wilkinson Microwave Anisotropy Probe, which operated for about a decade from a launch in 2001 and released its final 9-year-long data set just at the end of 2012. And this is one of their final pictures. What I'm here to tell you a little bit about is the European successor to WMAP, which defines the current state of the art in cosmic microwave background studies, which is the Planck satellite. The Planck satellite was launched in 2009. This is Europe's spaceport in French Guiana. I must admit I hadn't been aware up until that point that Europe had a spaceport, but it apparently does have a spaceport. It's a very long project. Planck was initiated around 1995, 1996, and so it took about 13 years to get to the stage where it was ready to launch. There, I joined the project in about 1998 or so, when it was, I think, still supposed to launch around 2003 or 2005. In the end, it took a little bit longer than that to get everything together. But by 2009, everything was ready to go, and it was stuck on the top of a rocket and successfully launched into orbit. Not, in fact, orbit around the Earth, but an orbit around the Sun, the so-called Earth-Sun Lagrange 2 point. So it's an orbit outside the orbit of the Earth, going around the Sun. I was only watching this on videocast, which was quite unnerving enough for me. Quite a lot of the Planck satellite collaboration actually went to Kourou to watch it in real life, and apparently it's terrifying to see 10 years of your life's work stuck on the top of a giant firework and then blasted off into space. But luckily all went very, very well, and then since that launch, the satellite's been taking lots of data, and that led to culmination in the first cosmology results being released earlier this year, in March of this year. The original intention of the satellite was that it would carry out 2 surveys of the sky. It takes 6 or 7 months for it to look at the entire sky. It sort of spins around, and as it spins, it twists, so that eventually it covers the whole sky. In the end, it did much better than we thought. It lasted for long enough to do 5 sky surveys rather than just 2, so we have much better data, in fact, than we thought. So the release that we've made in March 2013 is just the first data release for cosmology from the Planck satellite, containing the first 2 sky surveys, and next year there should be a release of further data, which will also include measures of the polarization of the light as well as its temperature. So there's a bunch of stuff in this data release, which I'll go through very quickly. There's maps of the sky, so measuring the microwave background, just making a map. As I say, these are the photographs of what the young universe looked like. There's catalogs of sources. You can see galaxies and microwaves. And then there's the cosmic microwave background itself, and then there's a whole pile of papers that describe the results which have been obtained so far from that. I'm only going to be able to touch the surface of all of that large amount of data and analysis and hard work by the collaboration. So these are the basic pictures. These are different frequencies of microwave radiation. The way to think about this is when you're working with visible light, you've got different colors. You can look in red or in green or in blue there. And if you observe in different colors, you can learn different things about objects depending what color they are. The microwave background is basically the same. Here we have 9 different frequencies. So these are the microwave equivalents of the colors of the rainbow, ranging from really the radio part of the spectrum up in the top left and into the far infrared part of the spectrum at the bottom right of this picture. What you can see is the pictures kind of change their nature as you go along. In all of them, you can see a horizontal band along the middle, and that's indicating emission from our own galaxy. If you think about the Milky Way galaxy, if you were to look up in the night sky, you can sometimes see the Milky Way galaxy as a kind of plane in the sky where all of the stars are. There's also lots of dust in that region as well, which means that the Milky Way emits in the microwave from cold dust, as well as brightly from stars and visible light. And so this is just the microwave version of the Milky Way being seen here. In the infrared channel right down at the bottom right there, you see a lot of stuff going on because that channel is very sensitive to emission from dust. But when you go to the lower frequency channels, particularly the middle ones along the middle row, you can see there's not much contamination from the galaxy, but you can still see structures away. I should point it a little bit. You can still see structures here, which are the measures of the cosmic microwave background radiation, the primordial radiation. And what we want to do is then try to use these maps to subtract off all the stuff we're not interested in, like the galaxy, and leave behind the stuff we are interested in, which is the cosmic microwave background. Now, I appreciate the slide is not very clear, especially for people at the back, so rather luckily for me, there's an enormous poster here of the sort of thing that looks like when you do it. So this is a picture, the photograph of the young universe for you to look at. How does it compare to things we've seen before? Well, here's a comparison picture of the immediate predecessor, the WMAP satellite. I have to say, I think the European Space Agency press office must have put a lot of work into making the WMAP data look as bad as this, because the WMAP data is superb in itself, but somehow they managed to make it look a bit blurry, and you can see the higher resolution of Planck, best down at the bottom here. So this is kind of what I see if I take my glasses off. This is what I see if I put them back on again. And that's the difference between WMAP and Planck, is picking out that very fine structure. Now, I'm going to have a graph. I'm going to indulge myself with a graph, because this is the most fantastic graph you'll ever see, bar none. This is what's called the power spectrum of the cosmic microwave background, and it measures the size of the blobs as a function of angular scale. So how big they are is along this way, and how prominent they are is in this direction. And the only funny thing about the plot is that we put the biggest angular scales on the left, so this corresponds to extremely extended blobs, and we put all the fine structure down here on the right. Now, for those of you who are not too far back, you might actually, just from looking at this, have noticed that there's an awful lot of features which are about the size of my thumbnail. Everywhere I look, there are blobs that size. That's nothing to do with the way the thing's been printed. It's because really in the cosmic microwave background, there are lots of structures on particular scales. And these structures I've highlighted are on an angular scale of about 1 degree, and that's what corresponds to this very prominent peak here. What that's saying is there are lots of things that you can see whose size is about 1 degree. It's not nearly as prominent on very large scales. You can't see so many big blobs, but you also can't see so many small blobs either. Now, the amazing thing about this plot is the size of the error bars. If you can see them, these points have microscopic error bars, and you see a whole sequence of oscillations. So we're measuring this structure very, very precisely. And through these points goes a line. And the line's not a join the dots through the points line. The line is a theoretical prediction for where the point should lie. And you can see all of these peaks being matched to extraordinary precision by theoretical calculation. And that's what I mean about predictiveness, letting you believe that you've got a good physical description of what's going on. Now, when that theoretical prediction was made in the 1960s, there was not a single data point on that plot. Not one. And then later on, there were a few data points with big error bars. Now there are a huge number of data points, all with tiny error bars, and yet they're still all fit by that curve. And because of that, this is the most amazing graph you'll ever see. Well, the most amazing graph you can see today, in my opinion. So I'm going to zoom on a little bit because I think time is starting to run out. For a cosmologist, the wiggly line is nice, tiny error bars. The reason why you want to measure that is to try and pin down some of the properties of the universe. So these are back to the parameters I mentioned in the first place. This may be a bit detailed for some of you, but these are different things we might try to measure. This is the density of cold dark matter in the universe, and we want to measure it with some accuracy. These are the sort of numbers you get in the error bars, which many of you will be able to see are very, very small uncertainties. This is the density of baryons measured to about 1% accuracy, I think. Density of cold dark matter, not quite that good, but not far from it, and so on and so on. And that's extracted from the curve which I showed you. I'm just going to skip, I think, to this plot, which is a graphical illustration of some of the things that are measured. These are the densities. So this is the composition of the universe again. I showed you this plot earlier. Here is comparison of what WMAP thought and what Planck thought. Kind of similar, but not exactly the same. We've seen a little bit of drift in our results between WMAP and Planck. The dark energy slice of the pie has got a bit smaller. The other slices have got a little bit bigger there. But those are the measurements that we're seeking to make. I also want to very quickly mention this plot. It's going to be quite tricky. I'm going to say it very, very fast. This is not a picture of the cosmic microwave background, but this is a picture of gravitational lensing. I mention it only because this is, to my mind, the nicest new result from the Planck satellite. Hard to describe. I'm going to have a go. Galaxy, cosmic microwave background. Cosmic microwave background comes towards you, but it goes past the galaxy, which has a gravitational field. The gravity will bend the light. The light will go round the galaxy as it comes towards you, which will distort the pattern here. It's like you put a lens in front of this picture, and you see some distortion. Look all over the sky, and everything on the sky is distorted because the light's always coming through close to galaxies and other things. So what we don't see is really the pristine, perfect photograph of the cosmic microwave background. We see it distorted. It's a bit like looking through one of these fuzzy bathroom mirrors that you sometimes see to stop people peering in. For us, that's actually a bonus because as well as figuring out what the cosmic microwave background is, you can try and figure out what the lens was like. The lens is caused by all the matter in the universe, and this is a picture of all the matter in the universe. Different colors showing where there's more matter. I think the light is more matter, the blue is less matter, all the way to the cosmic microwave background, which is right across the universe. So this is an amazing picture showing you the distribution. It's not very high resolution. The blobs are quite big and fuzzy, but nevertheless, it's the first to have an all-sky map of this so-called gravitational lensing effect, and I think this could be a fantastic area for future cosmological studies. Okay, we're nearly done. What's next for Planck? Well, as I say, next year we'll have another data release. There'll be twice or 2.5 times as much data, more analysis, and also, realistically, the last analysis was a bit of a time-pressed mad panic leading up to results. And so hopefully, next time around, we will learn from those experiences and be able to do things a bit more systematically and get extra robustness out of the data. So, to end, status of observational cosmology. This is really, really good, I think. The precision measurements that we're making are extraordinary, and we're managing to build up what's really quite a simple model of the universe. Just a few parameters, like the densities of the different components, will let us explain those data and tell us what the composition of the universe is. There's also, in fact, strong evidence just from this picture that inflation did take place in the early universe, because inflation can predict the kinds of structures that we're seeing in the cosmic microwave background photograph. So that's all pretty fantastic. Unfortunately, I'm mostly not an observer, I'm mostly a theorist. So from a theorist, I'm not supposed to just look at that pie chart and say, look how well I've measured my pie. I'm supposed to take my pie and explain why the pie is made up of the things it's made up of. So I have a look at that picture. It's got baryons, it's got dark matter, and it's got dark energy. So I think about that. Well, we don't know why the universe is all matter and not antimatter, which is what the baryon density measures. We don't know what the dark matter is, though we hope we might sometime soon. And we don't know what the dark energy is. So, theoretical cosmologists have got a little bit more work to do, I think. So finally, last slide is to mention one way in which this might change. Just by lucky coincidence, a new project that I'm involved in called the Dark Energy Survey is trying to address the dark energy in the universe and learn more about its properties in order to try and unpick that part of the puzzle. It's a 5-year project led from the US with lots of involvement from us in the UK as well. It just so happened that this 5-year project began this week. It started on Saturday. And these are some early photographic images, which are probably rather hard to see here, but maybe you can see more clearly on the webcast later on. So in a few years' time, hopefully we'll have some results from that, and that might be further observational input that might help us hard-pressed theorists figure out the answers to some of these questions on my last slide. Thank you very much.